there is a question that has drifted, very quietly, through the back rooms of physics for more than half a century. It is not a question that announces itself. It does not appear in the headlines of new discoveries, except very rarely, and even then in carefully hedged language. It is one of those questions that physicists sometimes raise with each other late in the evening, after the proper business of the day is done. A question that is taken seriously, and yet held at arm's length, because no one is quite sure what to do with it. The question is simply this: what if the universe is inside a black hole? Not a black hole that contains a small piece of the universe. Not a black hole that we might fall into, somewhere out among the galaxies. The universe itself, everything we can see, and everything beyond what we can see. Every star, every galaxy, every cold drift of gas in the empty places between them. All of it, the entire visible cosmos, sitting quietly inside the interior of something far larger, in some other space, in some other arrangement of things. It sounds, on first hearing, like the kind of idea that belongs in a story rather than in a journal of physics. And yet the mathematics of it has been worked out, again and again, by serious people, over a span of decades. There are reasons to consider it. There are coincidences in our measurements that, if pulled at gently, begin to suggest it. There are theoretical models, several of them now, that lead to it from different starting points. None of them is proven. None of them is ruled out. This is what we are going to drift through tonight. Slowly. There is no hurry. The idea has been waiting for 50 years. It will wait a few more hours. We will look at where this thought came from, and at the strange numerical coincidence that first suggested it. We will look at what the inside of a black hole actually is, in the language of general relativity, and at how it differs from the inside that most people imagine. We will follow the small group of physicists who have, in different ways, tried to take the idea seriously. And we will see what kinds of universes they have built, on paper, when they begin from this assumption. We will look at one recent observation that may, or may not, be a faint signature of such a universe. And we will arrive, eventually, at the deep questions that no one yet knows how to answer. The night is long enough for all of this. Settle in. There is nothing here that needs to be rushed. The universe, whichever kind of universe it turns out to be, will not change its nature in the next 2 hours. It is worth noting, before we begin, that this is not a fringe idea. It is not the kind of speculation that lives only on the dim edges of physics. It has been published in respectable journals: Nature, Physical Review D, the monthly notices of the Royal Astronomical Society, and the Universe Journal of the European Astronomy Community. Its proponents include physicists with full appointments at established institutions, working in the same buildings as their more conventionally inclined colleagues, attending the same conferences, reviewing the same papers. The hypothesis is one of several alternatives to the standard cosmological picture that are currently being explored. It is not the leading alternative. It is also not a reject. It sits in a kind of middle zone, taken seriously by some, considered improbable by others, treated by most as one more option in the wide menu of possibilities that modern cosmology has to consider. This middle zone is, in some ways, the most interesting place in physics to spend an evening. The settled questions are, by definition, settled. They have been answered, sometimes magnificently, but the work of answering them is mostly done. The completely unsettled questions, on the other hand, are sometimes too unsettled to think about clearly. There is too little to grip. The middle zone is where the work is happening. It is where careful arguments are being made, tested, and refined. It is where, If a real shift in our picture of the cosmos is going to come, it is most likely to come from. So we begin where the question itself began, with a very simple piece of arithmetic, performed quietly on a piece of paper, sometime in the early 1970s. In 1972, a physicist named Raj Pathria published a short paper in the journal Nature. It was barely 2 pages long. It carried the title simply, "The Universe as a Black Hole." Around the same time, working independently, the British mathematician I.J. Good arrived at a similar idea. Neither of them claimed to have proved anything. They were pointing out, instead, a curiosity, a coincidence in the equations. The coincidence had to do with a length. 2 lengths, in fact, that ought, on the face of things, to have nothing to do with each other. The first length was the radius of the observable universe. The distance light has had time to travel since the beginning, the boundary beyond which we cannot see. This is a number that grows over time, as the universe ages, and as light from more distant regions arrives. Today, in the units physicists prefer, it is something on the order of 10 to the 26 meters. About 46 billion light-years when measured in proper distance, after accounting for the expansion of space. The second length was something quite different. It was the Schwarzschild radius, a number that comes from the theory of black holes. If you take a given mass, and you ask how small a sphere you would have to compress that mass into for it to become a black hole, the answer is the Schwarzschild radius. For the Sun, that radius is about 3 kilometers. For the Earth, less than a centimeter. For a galaxy, it might be measured in light years. Pathria and Good asked a simple question. What if you took all the mass in the observable universe? Every star, every dust cloud, every black hole, every faint trace of gas, and you calculated the Schwarzschild radius for that total. How big would it be? The answer was unsettling. The Schwarzschild radius of the mass of the observable universe is, very nearly, the same as the radius of the observable universe itself. The 2 numbers, drawn from completely different parts of physics, are the same to within the precision of measurement. Now, one can argue about whether this is a deep coincidence or a shallow one. Many physicists have. Some have pointed out, quite reasonably, that it follows from the fact that the universe is approximately flat, and that flatness is itself a condition closely related to the kind of geometry one finds at the edge of a very large black hole. Others have argued that this is precisely the point. The universe is flat because it is the interior of a black hole and not the other way around. This will be a thread we return to. For now, only this. The radius of the observable universe is, to the precision of modern measurement, equal to its own Schwarzschild radius. By the standard definition of a black hole, a region from which the escape velocity exceeds the speed of light, the universe meets the criterion. We are inside a sphere whose escape velocity, from any point within it, exceeds the speed of light. In one of the simplest formulations of the question, that is, what it means to be inside a black hole, and in one of the simplest formulations, we already are. Pathria's paper was modest in tone. He described a closed Friedmann universe, a universe with positive curvature, a universe that, in Einstein's equations, naturally curls back upon itself. And he showed that under certain conditions this kind of universe could be matched, mathematically, to the interior of a Schwarzschild black hole. The exterior of the black hole was someone else's universe, a larger one, a parent. The interior was ours. He did not insist on the picture. He offered it as a possibility, a model among models. He noted that several long-standing problems in cosmology, the question of why the universe was bounded, the question of why its parameters seemed so finely chosen, would dissolve if the universe were the inside of a black hole, rather than something arising out of nothing. The paper was read, quietly, and then largely set aside. Cosmology had other concerns in the 1970s. The Big Bang model was being refined. The cosmic microwave background had recently been discovered. The era of inflation was about to begin. The idea of the universe as a black hole became one of those quiet curiosities that surface every few years in a different paper by a different author, often with no awareness that the thought had been thought before. This is, in fact, a common pattern in theoretical physics. An idea is proposed. It is read by a few people. It is filed away. Years pass. Someone else thinks of it independently, often using slightly different language. The new version is published, read by a few people, and filed away. Years pass again. A third person notices that there is a connection between two earlier papers and writes a synthesis. The synthesis is read by a few more people, and so on through cycles, until either the idea matures into a proper research program with its own community of practitioners, or it fades into the background, becoming part of the general furniture of theoretical physics, known to specialists, occasionally referenced, but not actively pursued. The universe inside a black hole idea has, over the decades, hovered between these states. It has never quite become a major research program. It has also never quite faded. It has been kept alive by a small but persistent group of thinkers, each adding their own variations, each finding something in it that others had not. The pattern of patient, intermittent attention is part of what gives the idea its character. It is the kind of question that has been considered carefully by careful people for a long time without ever being resolved. But it never quite went away. And it has, in recent years, returned. Before we follow it further, though, we should slow down for a moment and look at what is actually meant by the word interior when we are speaking of a black hole. Because the interior of a black hole, in the equations of general relativity, is not what most people picture when they hear the word. It is much stranger than that. And once we see what it really is, the idea that a universe could fit inside one becomes, perhaps, a little less surprising. So that is where we will go next. Through the horizon, slowly. There is no danger in it. We are only following the mathematics. The interior of a black hole, in the simplest case, is described by something called the Schwarzschild solution to Einstein's field equations. Carl Schwarzschild wrote it down in 1915, while serving as an artillery officer on the Russian front in the First World War. He had volunteered for service when he was already over 40. Despite being in poor health, despite being one of the foremost astronomers in Germany, he had been director of the Astrophysical Observatory in Potsdam since 1909. He had no need to enlist. He did so anyway. In December of that year, just a few weeks after Einstein's general theory of relativity was published, Schwarzschild, working in his spare hours, between the calculations of artillery trajectories that were his official duty, wrote down the first exact solution to Einstein's field equations. He sent it to Einstein in a letter dated the 22nd of December, 1915. "As you see," he wrote, "the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." It is a remarkable sentence, written from the front, with shells falling. The land of your ideas. He treated mathematics in the dark of a winter campaign as a place to walk in. He died a few months later, in May of 1916, from a rare autoimmune skin disease that had begun while he was at the front. He was 42. He never saw his solution become famous. He did not live to see what was inside it. The geometry he had written down would take physicists more than 4 decades, working at peace, to fully understand. What Schwarzschild showed was that, around any non-rotating spherical mass, space-time curves in a particular way, a way that depends only on the mass. If the mass is concentrated within a small enough region, within its own Schwarzschild radius, then the geometry of spacetime develops a peculiar feature. There is a surface, at that radius, beyond which all paths through space and time lead inward. Outside the surface, a particle can move toward the center or away from it. Inside the surface, it cannot move away. Every path, every trajectory, every direction it might choose to travel leads further in. This is the event horizon. It is not a physical wall. There is nothing there that you would feel if you were to cross it. For a sufficiently large black hole, you would not even notice the crossing. The tides, the curvature, the local geometry, all of it would seem ordinary at the moment of passage. The horizon is defined not by what is local, but by what is possible. It is the boundary at which the future no longer contains the outside. What is strange, though, is what the equations say happens inside. Inside the horizon, the roles of space and time, in a precise mathematical sense, exchange. The radial coordinate, the coordinate that tells you how far you are from the center, becomes time-like, and the time coordinate, the one that ticks forward on your watch outside, becomes space-like. This is not a metaphor. It is what the metric, the mathematical object that describes the geometry of spacetime, actually says. The signs of certain terms flip across the horizon, and the two coordinates trade their characters. The consequence is that, inside the horizon, moving toward the center is not a choice. It is the passage of time itself. To resist falling toward the center would be to resist tomorrow. There is no more possibility of staying in place than there is, in our ordinary world, of staying in the present moment forever. The future, inside, points inward. It takes some time to absorb the strangeness of this. We are used to thinking of space as the dimension of choice, and time as the dimension of obligation. We can move left or right, up or down, forward or back, but we cannot move backward in time. Inside a black hole, this familiar division reorganizes. The radial direction, the direction that, from outside, looks like a spatial dimension, becomes the dimension along which one is obliged to move, and the dimension that, from outside, was time, becomes a kind of breadth. One can, in principle, move along it, but nothing requires one to. It is a kind of inversion of the ordinary world, not a contradiction, not an absurdity, just a different arrangement of which dimensions hold the obligation of forward motion, and which dimensions hold the freedom of choice. This is why the singularity at the center of a black hole, in classical relativity, is not best described as a place. It is, in the equations, more naturally described as a moment. A moment in the future of any observer who has crossed the horizon, a moment toward which all paths converge. And here is where the idea of a universe begins to fit in, because if the singularity is a moment, then everything before it, every space-like slice between the horizon and the center, is a kind of sequence in time. A history, the interior of a black hole, when properly described, has a structure not unlike a cosmology. There is something like an initial state near the horizon. There is an evolution. There is a kind of ending at what we would call the singularity, and this evolution looks, to certain mathematical eyes, very much like the story of an expanding or contracting universe. When one writes the interior of a Schwarzschild black hole in the right coordinates, the so-called Cantoscax coordinates, the metric looks like the metric of a closed, anisotropic universe, a universe that is, in one direction, contracting, in another direction, perhaps expanding, a universe with its own internal time. This was already known in the 1960s. It is part of the standard textbook on relativity. It is not speculative. It is simply what the equations say when one follows them past the horizon. What Pathria and Good noticed, what later authors would notice and develop, is that this internal universe might, under the right conditions, be matched to the kind of universe we appear to live in, a closed cosmology, expanding from a hot, dense beginning, evolving outward in something analogous to time. The beginning would not need to be a singularity in the usual sense. It would only need to be the moment inside the black hole when the interior universe began. It is a strange picture, worth pausing over. It says, in essence, that what we call the Big Bang, the explosive origin of everything, would not be an event that happened at a point. It would be a space-like surface near the horizon of a much larger black hole, in some larger space, in some larger universe. What we experience as the expansion of the cosmos would be the natural unfolding of geometry inside that horizon. The cosmic microwave background, the most ancient light we can detect, would be the light from a region nearer to the horizon than we are. The distant galaxies, racing away from us, would be racing along the natural geodesics of the interior. There would be no center. There would be no edge. From within, the geometry would feel exactly as ours does, like a universe. Consider the picture in a little more detail. From outside a black hole, the horizon is a sphere, a definite radius, a boundary in space that one approaches and crosses. From inside, this is no longer the right description. The horizon, viewed from inside, is in the past. It is the moment of crossing, the moment when the observer enters the interior region. Different observers, who entered the black hole at different times, share different pasts. Their horizons are not at the same place. They are at different times in their own personal histories. The exterior of the black hole, for an inside observer, is not a place that lies somewhere out there. It is a moment that has already happened. It cannot be returned. This is part of what is meant when physicists say that the inside of a black hole is more like a cosmology than a region of space. A cosmology is a story about time, about what happens after a beginning, about the unfolding of conditions across an interval. The inside of a black hole in the equations is exactly such a story. It begins at the horizon. It evolves toward the singularity. The space within it, at any given moment of the interior time, is a slice through that evolving history. Just as our universe, at any given moment of cosmic time, is a slice through the evolving history of all the matter and energy it contains. If we are inside a black hole, then the moment we call the Big Bang is the moment of formation of the black hole, viewed from inside. The 13.8 billion years that have elapsed since are 13.8 billion years of interior time. The galaxies racing away from us are racing along the geometry of the interior. The horizon, somewhere out beyond what we can see, is the boundary of the parent black hole, as seen from within. The singularity, in classical theory, would be in our future, the eventual end of our cosmos, the moment where the interior geometry collapses to a point. In quantum-corrected theories, the singularity is replaced by something else, and the picture is less stark, but the basic geometric idea remains. We are inside. There is a horizon. There is a beginning. There is, perhaps, an end, and the apparent age of that universe. The time since the beginning would correspond to a position on the time-like axis of the black hole's interior. The further along we are, the further from the moment of formation. the closer to the singularity in the simplest model, although in any realistic version, the singularity is not actually approached, because some other mechanism intervenes long before the geometry breaks down. To that mechanism we will come. For now, only this. The interior of a black hole in the equations of relativity behaves like a universe. It has its own time. It has its own evolution. It has its own beginning, and in the simplest cases, its own end. There is nothing in the standard mathematics of general relativity that forbids us from being inside one. Whether we are, of course, is another question. The mathematics permits the picture. It does not require it. There are other models, other arrangements of geometry that also fit the observations. But the picture is permitted. It is consistent. It is one of the things general relativity allows. And so, in the years after Pathria's quiet paper, a small number of physicists began to ask what such a universe would have to look like, what its rules would have to be, what kind of black hole, in what kind of larger space, would produce a universe that resembled ours. There were many ways to begin. Some began from the outside, asking what kind of parent universe was required. Some began from the inside, asking what physics, near what we call the Big Bang, would generate the observed properties. Some began from neither end, but from the middle, from the strange thermodynamics of black holes themselves, from the way information seemed to be preserved or lost across their horizons, from the way their entropy grew with their surface area rather than with their volume. Different starting points led to different destinations, and in each case, the destination was a particular kind of universe inside a black hole, a particular set of conditions, a particular signature, perhaps, that one might look for. We will visit several of these now. Slowly. The picture is not one picture. It is a family of pictures. Each one is related to the others, and yet each is its own meditation on the same underlying thought. In the late 1980s, an American theoretical physicist named Lee Smolin began to take the question of the universe inside a black hole in a quite particular direction. Smolin was not primarily a cosmologist. He worked in the field of quantum gravity. The long, difficult, still unfinished attempt to find a single theory that would unite Einstein's general relativity with the principles of quantum mechanics. Both theories are extraordinarily successful in their own domains. Both have been tested to extraordinary precision, but they do not fit together. They contradict each other in their basic assumptions about how reality is structured. The search for a theory that contains them both is one of the great open problems of modern physics. Smolin had a thought. Within general relativity, black holes contain singularities, points where the curvature of spacetime becomes infinite, where the equations themselves break down, where the predictions of the theory cease to make sense. Most physicists assumed that these singularities were not really there. They were artifacts of using the wrong theory in conditions where it failed. The correct theory, the as yet undiscovered theory of quantum gravity, would replace each singularity with something else, something finite, something well-defined. But what would it replace them with? Smolin's suggestion, made first in 1992 and developed in his book The Life of the Cosmos, was that the singularity inside each black hole, the place where general relativity fails, was a place where a new universe began, a bounce of sorts. A moment when the contracting interior of the black hole reached some maximum density, some Planck scale limit, and then expanded again on the other side into a new spacetime, a new universe, born inside the black hole, but causally disconnected from it. A child. This is the idea that has come to be known as cosmological natural selection, or sometimes the fecund universes hypothesis. The reasoning that followed from this starting point was strange, but careful. Smolin observed that each new universe, born from a black hole in a parent universe, might inherit something like the laws of physics of its parent, but with small variations, slight changes in the constants. Different masses for the elementary particles, different strengths for the fundamental forces. Most of these variations, like most genetic variations in biology, would lead to universes very different from any that were viable, universes that collapsed quickly, universes where stars never formed, universes where matter could not gather into structures, universes that, having been born, did very little and produced very few black holes of their own, but some variations, by chance, would produce universes more fertile than their parents, universes where black holes formed easily and abundantly. Stars in great numbers, going through their lives, collapsing into black holes at their endings. Each of those black holes produces another universe. Each of those universes, in turn, perhaps produces more black holes still. Over very long times, across very many generations of universes, the population of universes would shift. The ones that produced many black holes would produce many descendants. The ones that produced few would have few descendants. And so, by a process directly analogous to biological natural selection, the population of universes would come to be dominated by those whose physical constants happened to maximize black hole production. Our own universe, Smolin pointed out, appears to be remarkably good at producing black holes. The conditions required for stars to form, for those stars to live long enough to fuse heavy elements, for the heaviest of them to collapse into black holes at the ends of their lives. These conditions are quite finely balanced. Slight changes to the strength of gravity, or to the mass of the proton, or to the cosmological constant, would disrupt the chain. The universe would produce fewer black holes, or none at all, if our universe is the way it is, because that way produces lots of black holes. Then we have a kind of explanation for why the constants of physics take the values they do. They take those values because, in the long ancestry of universes, those values were favored. It is an unusual line of reasoning. It moves the question of why physics is what it is into a domain that resembles biology. It treats the laws of nature themselves as objects subject to a kind of evolution, and it makes, importantly, a prediction. Smolin argued that if cosmological natural selection is correct, then small changes to any of the parameters of physics should make the universe worse at producing black holes, not better. Our universe should sit at, or very near, a peak in the landscape of black hole fertility. This prediction has been the subject of considerable debate. Some have argued that small changes would, in fact, increase black hole production. Some have argued that the prediction is too vague to test. Smolin has responded again and again to these criticisms, refining his model, considering edge cases. The debate continues. It has not been settled. What is striking about Smolin's framework, beyond its specific predictions, is the way it shifts the question of cosmic origins. Most accounts of the Big Bang treat the universe as a single event, the beginning of everything, unique, unrepeatable. The question of why the universe has the properties it does, in such accounts, is either left to fundamental theory. Some still undiscovered law of physics will eventually explain it, or to anthropic reasoning. We observe the properties we do because only a universe with those properties could contain observers like us. Both of these answers have problems. The first kicks the can down the road. The second feels, to many people, more like an evasion than an explanation. It tells us we observe what we observe because if we observed anything else, we would not be here to observe it. This is true. It is also somewhat unsatisfying. Smolin's framework offers something different. It says that universes are objects with histories. They have parents. They have children. The properties that any given universe has are not given once and for all by some abstract principle. They are the result of a long descent, with modifications, from earlier universes. The reason our universe has the constants it does is that those constants are good for producing black holes. And the constants of universes have, over the long ancestry of cosmic things, drifted toward black hole-friendly values. The fine-tuning is not a coincidence. It is also not an inscrutable fact. It is the outcome of a process. Whether this process actually occurs is another question. Smolin has been clear throughout his career that his proposal is a hypothesis, not a confirmed theory. He has invited disproof. He has written more than once that he would be glad to see his idea ruled out, because that would mean physicists had learned something. The point of a scientific hypothesis, on his account, is not to be true. It is to be precise enough to be wrong about, and to spur the work that would make it wrong. This attitude, making proposals that one half hopes will be falsified, is one of the more admirable habits of theoretical physics. It is not the habit of the daily newspaper. It is also not the habit of certain branches of philosophy, where ideas are sometimes defended past the point of plausibility. Physicists are usually quite happy to see their pet theories disproven, because disproof clears the ground for new work. Smolin's hypothesis, in this spirit, has been put forward, refined, criticized, and refined again over more than 3 decades. It has not been disproven. It has also not been confirmed. It sits in the productive middle. The picture that Smolin offered of a universe that is one of many, born inside a black hole in a parent universe, descended from a long ancestry of similar births, and capable of giving birth in turn to its own children whenever a star collapses or a galactic core consumes too much matter, is a picture that has shaped the way many physicists think about cosmology. Even those who disagree with the details have absorbed something from the framework. The idea that universes might be plural, that they might be related, that ours might be one in a sequence, rather than a singular event. It is worth pausing on the scale of this picture for a moment before we move on. Our universe contains, by current estimates, somewhere on the order of 100 billion galaxies. Each large galaxy contains, on average, a supermassive black hole at its center, plus a population of smaller stellar mass black holes, perhaps tens of millions of them, scattered through the disk and halo. The total number of black holes in the observable universe is therefore very large. Tens of billions by some estimates, perhaps 100 billion, many more if one counts smaller objects. If each of these black holes contains, by Smolin's hypothesis, a daughter universe, then there are, descended from our cosmos alone, many, many billions of universes. Each of them, in turn, may contain billions of black holes, each containing a daughter universe of its own. The branching, over many generations, becomes very large indeed. This is not a picture meant to be visualized in detail. It is a picture meant to be carried lightly. The way one might carry the thought that the Earth is one planet among many planets, and the Sun is one star among many stars, and the Milky Way is one galaxy among many galaxies. The plurality at each scale was a surprise when it was first established. It became familiar only with time. Smolin's picture would, if true, add another level to the same long sequence. Universes, plural, most of them not very interesting. Some of them are interesting enough to contain stars, planets, and observers, and pages of equations, arguments, and patient inquiry. What this picture leaves unsettled is the question of mechanism. What exactly happens at the center of a collapsing star when general relativity says a singularity should form? What replaces the singularity in the correct quantum theory of gravity? What allows the bounce? Smolin's own approach to quantum gravity, loop quantum gravity, provides one possible answer. In that framework, space at the smallest scales is not continuous. It is granular. It is made of discrete loops or networks of geometric quanta. When matter is compressed beyond a certain point, the discrete structure of space resists further compression, the same way that the Pauli exclusion principle prevents electrons from occupying the same quantum state, and so makes ordinary matter incompressible beyond a certain density. Loop quantum gravity suggests that space itself is incompressible beyond a Planck scale limit. The collapse stops, the geometry rebounds, the bounce occurs, but there are other approaches, other mechanisms, other ways to imagine the singularity being avoided and a new universe being born in its place. We will turn to one of them now. A mechanism that requires no exotic quantum gravity at all, and that emerges from a small but well-known modification of Einstein's classical theory. Among the physicists who have taken the universe inside a black hole hypothesis most seriously in recent decades is a Polish-American theoretical physicist named Nikodem Popławski. He works at the University of New Haven in Connecticut. His papers on the topic have appeared steadily for more than 15 years. National Geographic and Science magazine in 2010 included his proposal in their lists of the year's top scientific ideas. Popławski's approach begins from a small modification of Einstein's theory of gravity. The modification is so small and so natural that many physicists regard it as a more correct version of general relativity in the first place. It is called the Einstein-Cartan theory. It dates to the 1920s, only a decade after general relativity itself. The Einstein-Cartan theory adds to Einstein's geometric description of gravity a property called torsion. Torsion is, roughly speaking, a twisting of spacetime. In ordinary general relativity, spacetime can curve, but it cannot twist. In the Einstein-Cartan extension, it can do both. The amount of twisting is determined by the spin, the intrinsic angular momentum of the matter within it. For ordinary matter at ordinary densities, the torsion is so small that it makes no observable difference. The theory is indistinguishable from standard general relativity in every test that has ever been performed. But at extraordinarily high densities, the densities that would prevail inside a black hole in the moments before a singularity would form a torsion behaves differently. According to Popławski's analysis, the spin of the fermions, the matter particles, generates a repulsive effect through torsion, a pressure that grows as the density grows, a pressure that, eventually, exceeds the gravitational pull that is causing the collapse. The collapse in this picture does not end in a singularity. It ends in a bounce. The matter, having reached a maximum density, rebounds. And what rebounds on the other side of the moment of maximum compression is not the original star. It is a new region of spacetime, a region that begins very small, very hot, and very dense. A region that, in the equations, expands. A universe, in other words, a new universe born from the moment of maximum compression inside the black hole, causally disconnected from the parent, growing on its own, following its own evolution, producing, eventually, its own stars and galaxies and black holes, and perhaps its own children in turn. Popławski has worked through the consequences of this picture in considerable detail. he has shown that the bounce naturally produces a period of rapid expansion, what cosmologists call inflation. He has shown that the universe born in this way would naturally appear, at large scales, to be flat and homogeneous and isotropic, just as our universe does. He has argued that the asymmetry between matter and antimatter, the fact that our universe contains matter at all, rather than having annihilated itself in a perfect balance of opposites, could be explained by tiny primordial black holes in the parent universe, devouring antimatter preferentially before our universe was born. He has even suggested that some of the dark matter we observe today might be remnants from this earlier era. What is striking about Popławski's model is its economy. It does not require new particles. It does not require new forces. It does not require any of the speculative additions that other cosmological models invoke to solve their problems. It uses only general relativity, with the modification of torsion that has been on the books for a century, and that many physicists already consider the more natural version of the theory. From this small adjustment, the picture of a universe inside a black hole emerges almost as a consequence. There is a particular elegance to this kind of argument. It does not propose a new substance, or a new field, or a new principle. It takes the existing theory, points out a feature that has always been there but rarely emphasized, and shows that this feature, if followed carefully, leads to a different cosmological picture, the same equations, a different reading, the way one might read the same poem twice and find on the second reading something that the first reading had missed. In Popławski's analysis, the bounce inside a forming black hole produces an enormous amount of matter through quantum particle production. The very strong, very anisotropic gravitational fields that prevail near the bounce do work on the quantum vacuum, generating new particles where none existed before. This is not a violation of conservation. The energy comes from the gravitational field itself. The newly created particles, in vast numbers, populate the new universe. They provide their initial heat. They constitute the matter that will, over the next billions of years, gather into stars and galaxies, and the people sitting up at night thinking about cosmology. This kind of particle production in strong gravitational fields is not Popławski's invention. It is a known process, predicted by quantum field theory in curved spacetime. The same process underlies Hawking radiation, the slow leakage of energy from a black hole's horizon, predicted by Stephen Hawking in 1974. In Popławski's picture, the Big Bang inside a black hole is, in a sense, an extreme version of the same physics. Quantum fields in regions of intense gravitational curvature do not stay empty. They produce particles. In a black hole that is just forming, the curvature is strong enough that this production is enormous. The result is a hot, dense, particle-filled new universe. This new universe, having been born hot and dense, expands. It cools. Over time, it dilutes, the particles thin out, and the temperature drops. Stars form, galaxies form. The whole long story unfolds on the inside of a horizon that, from the outside, would still look like an ordinary black hole. It is a picture that, once seen, is hard to forget. The black hole, viewed from outside, sits there. It absorbs matter. It radiates faintly. It does what black holes do. Inside, on the other side of the horizon, an entire cosmic history is playing out, all of it invisible to anyone outside, all of it cut off by the one-way membrane of the horizon, all of it perfectly compatible with the exterior simplicity of the object. Whether it is the correct picture, of course, remains an open question. There is no direct way to test it. The bounce, if it occurred, would have happened at the very beginning of our universe, in a state from which no signal can reach us. The parent universe on the outside of our containing black hole is causally cut off. We cannot observe it. We cannot send anything to it. We cannot receive anything from it. The horizon, by its definition, is a one-way membrane, but there are indirect tests, possible signatures, patterns in the cosmic microwave background that might, very faintly, carry the imprint of a bounce rather than a singular beginning, specific predictions about the geometry of the universe, whether it is exactly flat or very slightly curved. Specific predictions about the early conditions before inflation that distinguish a bounce from a singular start. These signatures are subtle. They are at the edge of what current instruments can detect. Some upcoming missions, the European Space Agency's planned ARRAKIHS mission, for instance, which will study dark matter structures, may eventually offer evidence one way or the other. For now, the picture is consistent with what we observe. It is consistent with what we know. It is one of the possibilities. It is worth pausing for a moment on the question of inflation, because it sits at the heart of the comparison between the standard cosmological model and the various bounce models we have been discussing. Inflation is the name given to a period of extremely rapid expansion that, in the standard model, took place in the very early universe, a tiny fraction of a second after the Big Bang. During inflation, in the standard story, the universe doubled in size many times, very quickly, before settling down into the slower expansion we observe today. Inflation was proposed in the early 1980s by Alan Guth and others to address several puzzles in cosmology. Why is the universe so flat? Why is it so homogeneous, even between regions that have never been in causal contact? Why, on the largest scales, does it look so smooth? Inflation, by stretching the universe out enormously in its earliest moments, smooths everything that is not the largest scale fluctuation. It explains the flatness, the homogeneity, and the absence of certain exotic relics that simple Big Bang models predicted. The picture is well supported by observation. The patterns in the cosmic microwave background match the predictions of inflation to high precision. Most cosmologists today regard inflation as a real feature of the early universe, even though the precise mechanism, what field drove the inflation, what ended it, what its detailed properties were, remains an active area of research. In the bounce models we have been discussing, inflation does not need to be added separately. It comes naturally with the bounce. The same dynamics that drive the rebound from maximum compression also drive a period of rapid expansion. Popławski's torsion bounce produces inflation. Gastignaga's exclusion principle bounce produces inflation. Loop quantum gravity bounces produce inflation. The mechanisms differ, but the result is similar: a short period of rapid expansion, followed by a slower expansion, followed by the long evolution of the cosmos. This is one of the appealing features of the bounce models. The standard model needs to introduce inflation as a separate ingredient, a new field, a new energy, a new piece of physics that switches on for a moment and then switches off. The bounce models do not need this. They get inflation for free, as a natural consequence of the dynamics that prevent the singularity. Whether one finds this appealing depends on one's taste in physics. Some physicists like minimalism. They prefer theories that introduce as few new pieces as possible. Some physicists like specificity. They prefer theories that introduce new pieces only when those pieces have observable consequences. The standard model is more specific in its predictions about inflation than the bounce models are. The bounce models are more economical in their assumptions. Both approaches are legitimate. Both are being pursued, and in 2025, a new variant of this kind of model attracted attention when a research group at the University of Portsmouth, led by Enrique Gastiñaga, published a paper in the journal Physical Review D, proposing yet another mechanism by which the universe might have begun inside a black hole. Gastiñaga's approach is, in some ways, even simpler than Popławski's. It does not require torsion. It does not require any modification of general relativity at all. The mechanism that prevents the singularity in his model is one that physicists have known about for nearly a century: the Pauli exclusion principle. The Pauli exclusion principle states that no two identical fermions, no two electrons, no two protons, no two neutrons of the same kind can occupy the same quantum state at the same time. This principle is what gives ordinary matter its bulk. It is what stops a piece of stone from collapsing under its own weight. It is what stops the cores of dying stars from compressing endlessly. In the case of a white dwarf star, the dim, dense remnant of a sun-like star that has exhausted its fuel. It is the exclusion principle, acting on electrons, that holds the star up against gravity. In a neutron star, the still denser remnant of a heavier star's collapse. It is the same principle, acting on neutrons, that prevents further collapse. The exclusion principle generates a kind of pressure, a degeneracy pressure, a resistance to compression that arises not from heat, but from the basic quantum mechanical fact that fermions refuse to be squeezed into the same state. What Gastiñaga and his colleagues have shown is that, at sufficiently high densities, far higher than even neutron star densities, the exclusion principle would still resist further compression, even when ordinary degeneracy pressure has been overwhelmed. Even when the collapse seems irreversible by classical reasoning, the exclusion principle, applied carefully, produces a bounce. In their model, the universe began not from a singular Big Bang, but from a gravitational collapse in some larger universe that produced a very massive black hole, perhaps of order 10 to the 22 solar masses, about 1,000,000 billion times the mass of the Sun, followed by a bounce inside that black hole 25 billion years before the present. The bounce naturally produced two phases of accelerated expansion. The first, very brief, would correspond to what we call inflation. The second, ongoing, would correspond to what we call dark energy. Neither would require a new field. Neither would require a new substance. Both would emerge as consequences of the bounce dynamics. The universe born from this bounce would, in their analysis, be very slightly closed, slightly positively curved, like the surface of a very large balloon, rather than perfectly flat. This is a testable prediction. Current measurements are consistent with both perfect flatness and very slight curvature. Future measurements may decide between them. What unites these various models, Smolin's, Popławski's, Gastiñaga's, and others, is a shared vision. The Big Bang in this vision is not the beginning of everything. It is a transition, a bounce, a doorway. On one side, a black hole in some larger space in some other universe. On the other side, a new region of spacetime expanding outward, full of matter and energy, evolving over billions of years into the cosmos we now see around us. Our universe. What unites them also is a kind of humility. Each acknowledges that we cannot see past our own horizon. The parent universe, if it exists, is not accessible to us. We can never visit it. We can never observe it directly. We can only reason about it from inside, from the way our own universe behaves, from the conditions that obtain in our own little corner of whatever larger structure we inhabit. And perhaps this is the right place to pause and to think about what it means to ask such a question at all. We are very small things. We are biological creatures, bounded by short lives and short attentions, looking up from the surface of one small planet at a sky we have only recently begun to map. The fact that we can pose questions about the structure of the universe at all is remarkable enough. The fact that we can pose them in a way that is mathematically precise, that connects to careful measurement, that admits of refinement and disproof. This is something that took many thousands of years to develop, and that even now is the work of a relatively small number of people, scattered across a handful of institutions. The question of whether we live inside a black hole is, in this sense, a question we are barely equipped to ask. It strains our intuitions. It runs against our ordinary picture of where things are. It requires us to imagine the entire visible cosmos as a small interior in some larger arrangement, and to imagine that arrangement, in turn, as one item among many. There is no clear way to confirm such a picture from inside it. There is no clear way to refute it. We can only reason carefully about what would have to be true if it were the case, and what would have to be true if it were not. That perhaps is enough for one night. We do not need an answer. The thought itself is the substance. So we drift on to the coincidence at the heart of this whole subject, the strange fact that the universe seems to have already the dimensions of a black hole, and to what that coincidence might or might not mean. We have already mentioned, briefly, that the Schwarzschild radius of the mass of the observable universe is, very nearly, the same as the radius of the observable universe itself. It is worth coming back to this number and looking at it more carefully, because it is the seed from which the whole conversation grows. And because, depending on how one looks at it, it is either one of the most striking coincidences in physics, or it is barely a coincidence at all. The radius of the observable universe, expressed in meters, is something on the order of 4.4 times 10 to the 26. That is a number with 26 zeros after the 4.4, about 46 billion light-years, when measured in proper distance. The distance an object would have today, if you could pause the expansion of space and lay a ruler along the way. The total mass energy of the observable universe is harder to pin down precisely, because it depends on assumptions about dark matter and dark energy, and how to count them. But a typical figure is something on the order of 10 to the 53 kilograms. A few times 10 to the 53, depending on how generous one is with the inclusions. The Schwarzschild radius for a mass m is given by twice g times m, divided by the speed of light squared. G is the gravitational constant. The speed of light is well known. When you put in the numbers for the mass of the observable universe, you get a Schwarzschild radius of, again, something on the order of 10 to the 26 meters. The two figures agree to within the precision with which we know the inputs. Now, there are two ways to react to this. The first is to be amazed. The radius of the observable universe is set by the speed of light and the age of the universe. The Schwarzschild radius is set by the mass and the gravitational constant. These are entirely different physical considerations. The age of the universe has nothing to do with the gravitational constant in any obvious way. The fact that they conspire to give the same answer is, on the face of things, deeply strange. The second reaction is to point out that the two quantities are related, after all, by way of the cosmological model. In a flat universe, a universe with the so-called critical density, the equations of cosmology require a specific relationship between the mass-energy density, the rate of expansion, and the geometry. Working through that relationship, the equality of the radius of the observable universe and its Schwarzschild radius turns out to be a mathematical consequence of flatness. Given that the universe is observed to be flat, or very nearly so, the equality of the two radii is not surprising at all. Both of these reactions are correct. They are not in conflict. The equality follows mathematically from flatness. But the question of why the universe is flat is itself a deep question, one that the standard cosmological model addresses through inflation, but does not in any final sense explain. The equality is not, in this sense, an accident. It is also not, in this sense, fully understood. Where the universe inside a black hole hypothesis enters is in offering a different angle on the same equality. If the universe is the interior of a black hole, then its boundary should naturally be the Schwarzschild radius of its contents. This is just what a black hole interior looks like, geometrically. In this picture, the equality is not a coincidence at all. It is a definition. The universe is bounded by its Schwarzschild radius because that is what it means for the universe to be inside a black hole. The flatness of the universe in this picture is also explained. The geometry of the interior of a sufficiently large black hole, viewed from inside, is approximately flat over reasonable distances, just as the surface of the Earth, viewed from the ground, is approximately flat over reasonable distances. The horizon problem of cosmology, the problem of why distant regions of the universe, which have never been in causal contact, nonetheless share the same temperature and the same large-scale structure, would also be addressed. They share the same conditions because they were all part of the same interior, all the way back to the moment of formation. And the apparent fine-tuning of the cosmological constant, the strange smallness of the dark energy, which is many orders of magnitude smaller than naive estimates from quantum field theory would, in a black hole cosmology, be related to the size of the parent black hole. The larger the parent, the smaller the cosmological constant inside. These are appealing properties. They do not prove the picture, but there are reasons that physicists keep returning to it. Each time someone takes the picture seriously, they find that some long-standing cosmological puzzle becomes a little easier to think about. Not solved, but framed differently, made more tractable. There are also problems, important ones. The picture does not explain, for instance, what exists outside the parent black hole. Is there an infinite regress of universes, each inside a black hole and the next one out? Is there a bottom level, a primordial something, that is not contained in anything else? Both options have difficulties. The infinite regress raises questions about how anything could have started. The bottom level requires us to admit, eventually, a universe that was not born from a black hole, and to say something about how it began. The picture also does not, at the moment, make many sharp predictions. Most of its consequences are consistent with what we already observe, but they are consistent in a way that does not single the picture out. Other models also predict flatness. Other models also predict a homogeneous and isotropic universe. The hope is that, with enough refinement, the picture will eventually predict something that other models do not, some signature, some pattern, some specific value that can be measured, and that will distinguish it from competitors. For now, the picture sits in a kind of suspended state, permitted by the equations, suggested by certain coincidences, worked out in detail by a small but persistent group of physicists, neither confirmed nor refuted, waiting. It may help, before we go on, to give some sense of the scales involved. We have been speaking of the universe as the interior of a black hole large enough to contain everything we can see. How large would such a black hole have to be? The answer is that it would have to be enormous, by any standard we are used to. The Schwarzschild radius of the observable universe is, we have said, on the order of 10 to the 26 meters, about 46 billion light-years. The mass involved is around 10 to the 53 kilograms, perhaps a few times that, depending on assumptions about dark matter. This is many orders of magnitude larger than any black hole we have ever observed in the universe. It dwarfs even the most extreme objects we know. To get a sense of the gap, consider some of the largest known black holes in our cosmos. The black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million suns. The black hole at the center of the galaxy Messier 87, the first to have its image directly captured, has a mass of about 5.5 billion suns. The most massive black hole we have detected, the one powering the quasar Ton 618, located more than 10 billion light-years away, has a mass of somewhere between 40 and 66 billion suns, depending on the estimate. Its event horizon, by some measures, is about 1,300 astronomical units across, more than 60 times the distance from the Sun to Pluto. These are enormous objects. Ton 618, by itself, contains as much mass as all the stars in our galaxy combined. And yet, even at its mass, it is many orders of magnitude smaller than the black hole that would be required to contain the observable universe. The hypothetical parent black hole, if it exists, would have to be larger than Ton 618 by a factor of something like 10 to the 12. A trillion times larger, or perhaps more, depending on which estimate of cosmic mass one uses. This is not a black hole that resembles anything we have ever seen. It is a black hole on a different order of size altogether. It would not be embedded in any galaxy. It would not be powering any quasar. It would, in fact, be larger than any structure we know how to imagine. Its parent universe, the one that contains it, would have to be larger still, large enough that this enormous black hole was just one ordinary feature of its landscape, the way a stellar mass black hole is an ordinary feature of ours. This is part of what makes the picture so vertiginous. We are imagining structures larger than any structure we have ever observed. Larger, perhaps, than any structure that could fit within our framework of observation. The parent universe in this picture contains our universe the way our universe contains a sand grain. We are, on this scale, very small. It can be steadying in a way to feel small in this manner, the kind of smallness one feels looking up at the stars from a dark field at night, multiplied many times. The smallness of being not only one observer in one galaxy, in one cluster of galaxies, in one filament of the cosmic web, but also being inside one structure within a larger structure, within a still larger structure, in a sequence that may, for all we know, extend further than we can imagine. It does not have to be true. It may not be. Many cosmologists think it is not. But the size of what is being contemplated when we contemplate it is part of what gives the question its quiet weight. There is one recent observation, though, that has made some physicists wonder whether a faint trace of the picture might already be visible. We will turn to that observation now. It is not yet certain. It may turn out to be an artifact, an instrumental quirk, a statistical fluctuation. It is being argued about in the journals as we speak, but it is interesting enough to be worth describing, and it is a reasonable place for the night to drift onward. In March of 2025, a paper appeared in the journal Monthly Notices of the Royal Astronomical Society. The author was Lior Shamir, a computer scientist at Kansas State University. The title of the paper was technical, but the content was striking. Shamir had analyzed images of 200 and 63 distant galaxies, observed by the James Webb Space Telescope as part of its advanced, deep extragalactic survey. He had measured the direction of rotation of each of these galaxies. He had counted how many spun one way and how many spun the other. In a universe that is, on average, the same in all directions, a universe that has no preferred axis, no overall rotation, one would expect roughly equal numbers of galaxies spinning one way and the other, half clockwise, half counterclockwise, with respect to any chosen line of sight. Small fluctuations are expected, but the average should be very nearly 50-50. Shamir found something different. Of his 263 galaxies, about 158 rotated in one direction. About 105 rotated in the other. The split was not 50-50. It was closer to 60-40. 2/3, roughly, spun one way. 1/3 spun the other. The probability of finding a split this lopsided by chance in a truly random universe is small. Shamir estimated it at about 1%, not impossibly small, but small enough to deserve attention. What could cause it? There are a few possibilities, and Shamir discussed several of them in his paper. One possibility is observational bias. Our own galaxy, the Milky Way, is rotating. The Earth is rotating with it. When we observe distant galaxies, our motion through space produces small Doppler effects, slight shifts in the wavelength of the light we receive, depending on how the galaxy's rotation aligns with our motion. These shifts can affect how bright the galaxy appears to us. A galaxy whose rotation runs opposite to our own might appear slightly brighter than one whose rotation runs with us. And brighter galaxies are more likely to be detected. The asymmetry in observed rotations might therefore reflect not a real cosmic asymmetry, but a selection effect tied to our own motion. This is a real possibility. Shamir himself raised it. The Doppler-driven brightness difference would be small, much smaller, on the face of things, than the asymmetry observed. But the physics of galaxy rotation is not fully understood, and there might be amplification effects that current models do not capture. The selection effect explanation would not require any new cosmology. It would require only a more careful account of how we observe. The other possibility is more dramatic. The asymmetry might be real. The universe might, at large scales, have a preferred axis of rotation. If the universe were rotating as a whole, the rotations of individual galaxies would, statistically, be biased toward alignment with that overall rotation. Galaxies near the rotation axis would tend to spin one way more often than the other. The observed asymmetry would be a faint signature of this overall cosmic spin. A rotating universe is, in itself, an unusual proposition. The standard cosmological model assumes no overall rotation, but it does not require it. There are solutions to Einstein's equations. The Gödel universe, written down by Kurt Gödel in 1949, is the most famous that describe rotating cosmologies. They have always been mathematical curiosities. Nothing in the data has ever required them. If the universe were rotating, though, and here is where the connection to our main thread becomes interesting. One of the most natural explanations would be that it was born in a rotating black hole. Black holes, in general, rotate. Real black holes observed in the cosmos are rotating, most of them very rapidly. If our universe is the interior of a black hole, and that black hole was rotating at the moment of our universe's birth, then our universe would carry a preferred axis of rotation, inherited from its parent. The asymmetry in galaxy spins would be a kind of birthmark, a faint memory of the conditions in the parent. Shamir, in his paper, considered this explanation. He did not insist on it. He said only that it was one possible interpretation of the data, and that further observations would be needed to distinguish it from the alternatives. The reaction in the field has been measured. Some cosmologists have pointed out that earlier studies, with much larger datasets, did not find this kind of asymmetry. Some have argued that the JWST sample is too small for definitive conclusions, and that the apparent asymmetry could be a statistical fluke specific to this particular field of view. Some have suggested that the algorithm Shamir used to determine rotation directions might have biases that are hard to fully control for. Even with careful methodology, the Scientific American magazine published a thoughtful piece in April of that year, urging caution. The author noted that extraordinary claims about the structure of the entire universe require extraordinary evidence, and that we do not yet have it. Other cosmologists have been more receptive. Shamir's work is part of a longer pattern of similar findings, going back at least a decade, in which various sky surveys have shown statistically significant excesses of galaxies rotating in one direction or another. These findings have always been controversial. They have always been on the edge of significance. They have never quite been confirmed. They have also never quite gone away. What the JWST data does, perhaps, is to revive a question that had nearly been put to rest. Is the universe truly isotropic at the largest scales? Is there no preferred direction? Or is there, very faintly, a structure that hints at conditions present at the moment of our universe's birth? The question is open. It will probably take many more observations, with many more telescopes, over many more years, to settle it. The JWST is still young. Its surveys are still expanding. The number of distant galaxies we have measured carefully is small, compared to the number we will eventually measure. The truth, whatever it is, will become clearer. But it is, perhaps, worth pausing for a moment to appreciate what we are doing when we ask such questions. We are, in essence, looking at the rotation of distant galaxies. Galaxies whose light has been traveling toward us for billions of years. Galaxies that no longer exist in the form we now see them. And asking whether there is, in the orientation of their spin, a faint trace of the conditions that obtained at the very beginning of our universe. At the moment, perhaps, when our universe was young and small and only just formed inside something larger. It is a tenuous link, a subtle one. The data may dissolve under further scrutiny. The pattern may turn out to be a quirk of our own motion, or of our methods, or of the sample we have happened to study. It is not, by any means, a confirmation of anything, and yet there is something quietly remarkable about being able to ask the question at all. To examine, with instruments of our own making, the spin of galaxies so distant that their light is older than our solar system, and to wonder, from that data, about the geometry of our origin. Whatever the answer turns out to be, the asking is a kind of achievement, a small one, a patient one, the kind of thing that happens, slowly, over long careers, in offices full of computer terminals and printed papers and old coffee cups, while outside the seasons turn and the world goes on. Consider what the JWST is, for a moment. It is a telescope. A very large, very expensive, very carefully designed telescope, currently floating in space about 1 million miles from Earth, at a gravitational balance point known as the second Lagrange point. It was launched on Christmas Day of 2021. It took 6 months to reach its destination, to unfold its sunshield, to align its mirror segments, to begin its science operations. Since then, it has been doing what telescopes do, collecting light, very patiently, from very distant objects, and sending the data back to Earth. The light from the galaxies in Shamir's sample left those galaxies billions of years ago, when the universe was younger, when the stars in those galaxies were younger, when none of the things we now think of as solid had yet come into being. The light traveled all that time through the slow expansion of space. It arrived at the JWST mirror as a few photons, scattered across the detector in patterns that looked, to the algorithms that analyzed them, like spiral galaxies. From these patterns of light, after careful processing, after careful measurement of which way each spiral arm curved, after careful counting of how many of the galaxies spun this way and how many spun that way, a question about the geometry of the entire universe was formed, a question about whether we live, perhaps, inside something larger that itself rotates. This is what cosmology is, in practice. It is the slow accumulation of very faint signals, gathered with very expensive instruments, analyzed with very careful methods, and used to ask very large questions. The signals are faint because the universe is large and old, and the signals have to travel a long way to reach us. The instruments are expensive because the signals are faint and need to be detected with great precision. The methods are careful because the signals are easy to misinterpret. And because the questions are large enough that small errors in interpretation can lead to large errors in conclusion. We will leave the JWST observations there. We will let them rest. They are part of the conversation. They are not the conclusion. The picture continues to evolve. There is another thread we have not yet picked up, a thread that runs through much of modern theoretical physics, and that connects, in a somewhat different way, to the question of universes and black holes. It is the thread of the holographic principle. The holographic principle was first proposed in the 1990s by the physicists Gerard T. Hooft and Leonard Susskind. It grew out of a careful study of black hole thermodynamics, a subject that had been developing since the early 1970s through the work of Jacob Bekenstein, Stephen Hawking, and others. The puzzle that motivated the principle was simple and strange. When a black hole forms and matter falls into it, all the information about the matter, what it was made of, how it was arranged, what its history had been, appears from the outside to be lost. The black hole is described in classical relativity by only three numbers: its mass, its angular momentum, it's an electric charge. Everything else about what fell into it seems to be erased. This result is sometimes called the no-hair theorem, after a quip by John Wheeler, the same Wheeler who coined the phrase black hole in 1967. Wheeler said that black holes have no hair, meaning no distinguishing features beyond those three basic numbers. Whatever falls in, whatever its history, whatever its complexity, gets reduced to mass and spin and charge, and nothing else. But information in quantum mechanics is not supposed to be erasable. The basic equations of quantum theory are reversible. Given the present state of any system, the past should, in principle, be recoverable. If a black hole truly destroyed information, it would violate one of the deepest principles of physics. Hawking, in 1974, made the puzzle worse. He showed that black holes are not, in fact, perfectly black. They emit a faint thermal radiation, now called Hawking radiation, that arises from quantum effects near the horizon. Over very long times, a black hole can radiate away its entire mass and disappear. If it does, then everything that fell in is gone. The information, it would seem, is destroyed for good. This was the black hole information paradox. It was unresolved for decades. It is still, in some respects, debated. But one of the ideas that emerged from the long argument was the holographic principle. Bekenstein had shown, in the 1970s that the entropy of a black hole, a measure of the information it contains, is proportional not to its volume, as one would expect for any ordinary thermodynamic system, but to its surface area, the two-dimensional area of the event horizon. As if all the information about everything inside the black hole were somehow encoded on the boundary. This was, in itself, a strange result. Most thermodynamic systems we know of have entropies that scale with their volume. A box of gas, for example, has an entropy proportional to the number of particles in the box, which is in turn proportional to the box's volume. Doubling the size of the box with the same density of gas doubles the entropy. Bekenstein's result said that black holes do not behave this way. Their entropy scales with surface area. Doubling the radius of a black hole quadruples its entropy, not 8 times it. The information content of the black hole in this sense lives on its surface, not in its bulk. T. Hooft and Susskind generalized this observation. They proposed that the holographic principle applied not only to black holes, but to all of physics. The information content of any region of space, they argued, could be fully encoded on its boundary. The three-dimensional world we experience would be, in a precise mathematical sense, a kind of projection from a two-dimensional surface. A hologram. This sounds extreme. It is, but it has been worked out in a particular mathematical setting with great care. The setting is called the ADS/CFT correspondence, anti-de Sitter space and conformal field theory, and it was proposed by Juan Maldacena in 1997. It is today one of the most important and best-studied frameworks in theoretical physics. It provides a precise duality between a gravitational theory in a bulk region of spacetime and a non-gravitational quantum theory on the boundary of that region. The two theories describe the same physics in different languages. What this has to do with the universe inside a black hole is, perhaps, this. If the holographic principle is correct, then the information about what is inside any region of spacetime is encoded on its boundary. The information about what is inside our universe, then, would be encoded on whatever boundary our universe has. If that boundary is the event horizon of a parent black hole, then the information that constitutes our universe would, in some sense, be inscribed on that horizon. We would be the projection. The horizon would be the source. This is speculative. It connects two ideas, the universe inside a black hole and the holographic nature of physics, neither of which is established, and both of which are areas of active research. But the connection is not absurd. It is the kind of connection that physicists explore late at night, when they are trying to see whether two separate puzzles might be different facets of the same underlying truth. If the connection holds, then the universe as interior is not just a geometric fact. It is also an informational one. The universe is the interior, and the interior is a hologram, and the hologram is encoded on a horizon, and the horizon belongs to a black hole, and the black hole is sitting in some larger space, in some larger universe, where, presumably, the same kind of relationship holds again. It is, at this point, a tower of speculations. None of the levels is confirmed. All of them are being worked on. The mathematics is real. The physics is suggestive. The picture, taken as a whole, is one of the more interesting things human beings have ever tried to imagine. There is one further wrinkle, perhaps worth mentioning before we let the picture rest, and it concerns something physicists call a white hole. A black hole is, in the equations of general relativity, an object that things can fall into but never leave. It has an event horizon that admits inward motion only. A white hole is its mathematical opposite. It is a region of spacetime that things can leave but never enter. Its horizon admits outward motion only. The equations of general relativity, being time-reversal symmetric, allow for both. Whether white holes actually exist in nature is one of the long-running puzzles of theoretical physics. They have never been observed. The conditions required to form them, in classical theory, are exotic. Most physicists treat them as mathematical curiosities, solutions of the equations that may not have physical realizations. But there is a thread of cosmological thought, going back at least to the 1970s, that has wondered whether the Big Bang might have been, in some sense, a white hole. The geometry of the early universe, in its expanding outward from a hot, dense beginning, has an undeniable resemblance to the geometry of matter emerging from a white hole. Several physicists, including Carlo Rovelli and his collaborators, have explored this possibility within the framework of loop quantum gravity. Some have suggested that the inside of a black hole, after sufficient quantum gravitational evolution, transitions into the inside of a white hole, and that what we call the Big Bang in our own universe might have been the white hole face of a black hole from a previous cosmic phase. If the picture of the universe inside a black hole is right, then the bounce that birthed our universe could be described in either of two languages. From inside, it looks like a Big Bang, a beginning, a hot, dense state, an expansion outward. From a more careful geometrical view, in some models, it looks like the white hole side of a black hole to white hole transition. The same event, described from different perspectives. The black hole and the white hole are the two faces of a single object, glimpsed from different sides of time. This kind of duality is common in modern theoretical physics, two different descriptions of the same underlying reality, which emphasize different features. Each is correct in its own terms, each pointing at the same thing. Whether this particular duality reflects something real in our universe is, like everything else we have been discussing, an open question. But it is one more way of thinking about the same constellation of ideas. The universe is something contained. The boundary of containment is a horizon. The geometry of the boundary is both an exit and an entrance, depending on which way one looks at it. But we should not press it too hard. We have moved, in the last few minutes, from observations to mathematics to interpretations of mathematics. The further we move, the more uncertain the ground becomes. It is good to acknowledge that and to slow down. The question we began with was simple. Could the universe be inside a black hole? The answer, if there is one, is not simple. It is a layered thing. The mathematics permits the picture. Several different lines of reasoning lead to it. Some recent observations, very tentatively, may hint at it. Other recent observations are consistent with the standard cosmological model and require no such picture at all. Both possibilities are, at the moment, alive. The choice between them, if it can be made at all, lies in a future of measurements and refinements that we cannot, from where we stand, see clearly. For now, the cosmos is what it is. It expands, it cools, it evolves. The light from old galaxies arrives slowly after long journeys. The dark gathers. The stars turn on and burn and turn off again. Somewhere in all this, perhaps, the conditions of our origin are quietly recorded in the shape of the geometry, in the spin of distant galaxies, in the smallness of the cosmological constant, in patterns we have not yet learned to read. Or perhaps there is no record. Perhaps the universe simply is what it is, beginning as it began, without any larger frame to refer back to. Both possibilities are old. Both have been entertained by careful people. Neither has been ruled out. There is something steadying in this. The universe has been like this for a very long time. The questions about it have been like this for a long time, too. They are not going away tonight. They will not go away tomorrow. They will probably outlast us, and the people who come after us, and the people who come after them. Some of them may eventually be answered. Some of them may simply remain. Either way, they continue, like the stars, with a kind of patience that does not require anything from us. It is worth thinking, for a moment, about how slowly the universe moves by its own clock, and how quickly we move by ours. The universe, by current measurement, is about 13.8 billion years old. The Earth is about 4.5 billion years old. Life on Earth has existed for somewhere between 3 and 4 billion years. Mammals have existed for a couple of 100 million years. Beings recognizable as human have existed for a few 100,000 years. Civilizations capable of pondering cosmology have existed for a few thousand years. Schwarzschild's solution is 110 years old. Pathria's paper is a little over 50 years old. The James Webb Space Telescope has been operating for less than 5 years. Our entire history of asking questions about the cosmos in any organized way occupies a stretch of time so brief, on cosmological scales, that it would not register as a single tick. The cosmos does not particularly notice us. It does not notice anything. It simply continues, expanding, cooling, settling, rearranging its contents on timescales we cannot fully imagine. And yet, in this brief stretch, we have learned a great deal. We have measured the age of the universe to within 1%. We have mapped the cosmic microwave background to high precision. We have detected gravitational waves from black holes colliding billions of years ago. We have imaged the event horizons of black holes in distant galaxies. We have observed the rotation of 263 galaxies in a small patch of the early universe, and used the result to ask whether everything we can see is, perhaps, the interior of something larger. These are remarkable accomplishments. They are also, in the long view, a beginning. There will be more. There will be telescopes we have not yet built, observations we have not yet made, models we have not yet formulated. Some of them will overturn what we currently believe. Most will refine it. Whether the universe inside a black hole picture will survive these developments, or whether it will quietly fade as a more complete theory takes its place, is something we cannot know. What we can do, perhaps, is to hold the question lightly, to enjoy its strangeness, to appreciate the careful work that has gone into formulating it, to recognize that we are, all of us, very late arrivals at a very long evening, and that the questions we ask in our brief participation are one small part of a conversation that began long before us and will continue long after. We are nearing the end of what we set out to drift through. There is no urgency about reaching it. We can take the rest of the night slowly, the way one might walk home at the end of a long evening, without any particular destination in mind. The thought we began with is still here. It has not gone anywhere. It is one of the things one can carry quietly, like a small stone in a pocket, without ever fully understanding it. Imagine, for a moment, what it would mean if it were true, if we are indeed inside a black hole. What would actually be different from what we already see? The answer, in many ways, is nothing. The universe would still expand. The galaxies would still recede. The cosmic microwave background would still glow at its faint temperature. The stars would still age, and the planets would still orbit them. And the same long evolution from primordial gas to complex chemistry to whatever we are would still have unfolded on the same timescales, in the same way. The difference, if there is one, is in the framing. Not in what is happening, but in where it is happening. Not in the contents of the universe, but in its setting. The expansion we observe would be the natural unfolding of geometry inside a horizon. The flatness we measure would be a property of that interior geometry. The age we estimate would be a position along an interior time-like axis. The horizon at the edge of what we can see would be related, in some careful way, to the horizon of the parent black hole. And outside, somewhere in some larger arrangement of space and time, there would be perhaps a parent universe with its own physics, its own history, its own dark sky, its own slow turning, a place we cannot reach, a place we cannot hear from, a place that, if it is there, has no way to know that we are here, asking after it. This is not a frightening thought. It is not a comforting thought. It is simply a thought, one among many that the long history of physics has produced. It can be set down, gently, and considered, and set aside again. Nothing rests on whether one believes it or not. There is a kind of peace in this. The big questions of cosmology, where everything came from, what it is made of, where it is going, are old questions. They have been asked, in various forms, for as long as people have looked up at the night sky and wondered. Different ages have answered them differently. Different cultures have answered them differently. The current age has its own answers, refined by careful measurement and intricate mathematics, but it is not the final age. There will be other ages with other answers that will look back on ours the way we look back on the answers of older times, with respect, with affection, and with the sense that things have moved on. The picture of the universe inside a black hole may be one of the answers our age leaves behind. It may turn out to be true. It may turn out to be a step toward the truth. It may turn out, in the long run, to have been a productive mistake. The kind of idea that helps physicists think, even when it is wrong, by sharpening the questions that distinguish it from its alternatives. All of these are possible outcomes. None of them requires an answer tonight. What is more remarkable, perhaps, is the fact that we are able to think it at all. That we have built, over the last few centuries, a body of mathematics and observation careful enough to even pose the question. Pathria's 2-page paper in 1972 was a small offering. It took a long preparation, Schwarzschild's solution, Friedman's expanding universe, Hubble's measurements, and many others, for that small offering to be possible, and the developments that have followed, Smolin's evolutionary framework, Popławski's torsion bounce, Gastignaga's exclusion principle bounce, the JWST observations of distant galaxies. All of these required entire careers, entire institutions, entire networks of patient correspondence and shared instruments, and slow improvements in our understanding. The thought that the universe is inside a black hole is not, in this sense, a single thought. It is the cumulative result of many people, over many years, working quietly on different parts of an enormous problem. It is what happens when human curiosity is allowed, very gradually, to refine itself into something precise enough to be wrong about, and right about, and refined again. It is also, in a quiet way, a thought that is friendly to the question of our place. It does not tell us we are special. It does not tell us we are alone. It tells us, instead, that whatever we are part of a larger arrangement, embedded, contained, the interior of something in some sense, even if the something is not nameable in any familiar way. We are not a singular event in an empty void. We are, perhaps, one item among many, and our universe is one universe among many, and the history of cosmic things is a history with depth. Generations of black holes, generations of universes, generations of geometries, rather than a single moment of beginning. Whether the picture is correct in detail may not matter as much as one thinks. The mood of the picture is its own kind of contribution. It loosens the question of origins. It softens the demand for a single answer. It suggests that the why of everything may not be a why at all, but a how. How things turn out, in arrangements that contain other arrangements, in a way that does not need to bottom out at any particular level. There is something to be said for the company of these old, big, unanswerable questions. They do not require us to do anything. They do not require us to feel any particular way. They sit there available, the way the night sky sits available above whatever roof or canopy of trees one happens to be lying under. One can look at them when one wants to. One can let them rest when one wants to. The night, by now, is well along. The stars have moved across whatever sky is above the place where this is being heard. The galaxies have done what they do. Some of them, by some imperceptibly small fraction, may have rotated a little further along their long, slow turning. There is nothing more to add, really. The thought we set out with, that the universe might be inside a black hole, has been carried as far as it can be carried tonight. It has been turned over from several angles. It has been seen from the perspective of mathematics, history, observation, and speculation. None of the angles alone settles the matter. Together, they show us a kind of landscape, a region of possibility, a place where the question lives. We can leave it there. We can let it sit quietly, the way one leaves a window open at night and lets the air come in. Whatever the cosmos turns out to be, interior, exterior, singular, embedded, it will be the same cosmos in the morning, the same galaxies, the same long expansions, the same patient turning of things at scales much larger than ours. The Schwarzschild radius of the observable universe is, very nearly, the radius of the observable universe. The interior of a black hole, in the equations of relativity, behaves like a closed, expanding cosmos. The interior of our cosmos, in some models, behaves like the interior of a black hole. The two pictures meet in the middle, somewhere out beyond the limits of what we can directly observe. Smolin proposed that universes give birth to universes. Nikodem Popławski proposed that the bounce that begins each universe is driven by the spin of fundamental particles, twisting spacetime through torsion. Enrique Gastineaga proposed, more recently, that the bounce can be driven by the most familiar quantum principle. There is the simple refusal of identical particles to occupy the same state. Each model is different. Each makes slightly different predictions. None has been ruled out. None has been confirmed. The JWST has, perhaps, hinted at a small asymmetry in the rotation of distant galaxies. The hint may dissolve. It may strengthen. It is too early to say. The holographic principle suggests that the information about everything inside a region of space is encoded on its boundary. If the universe is inside a black hole, then the universe is, in some sense, a projection from a horizon we cannot see. These are the things we have been carrying tonight. They do not require any action. They do not require any conclusion. They are simply part of the long, slow, ongoing work of trying to understand where we are. There is one small image, perhaps, that one can carry away. The image of a horizon, not the horizon of the world where the sky meets the land. A different horizon, a geometric one, a boundary beyond which lies whatever lies. The light from inside cannot reach the outside. The light from outside cannot reach the inside. And yet, on either side of the boundary, something is happening. Stars are forming. Galaxies are turning. Time is passing in its strange, smooth way. We are on one side. The other side, if it exists, is the parent, the dark thing in which we are contained. It is not necessary to picture this clearly. It is only necessary, perhaps, to feel it. The sense of being held, the sense of being in some way inside. The galaxies continue. The cosmos expands. The horizon holds. The radio static of the cosmic microwave background, which is the oldest light in the universe, fills every direction at once, faint, and even, like the echo of an event we will never see directly, the echo of a beginning we will never reach. It is worth saying again, perhaps, and saying slowly, what an old picture this is. The cosmic microwave background was discovered by Arno Penzias and Robert Wilson in 1964, almost by accident, while they were trying to eliminate noise from a radio antenna in New Jersey. They could not figure out where the noise was coming from. It seemed to come from everywhere at once. Every direction they pointed their antenna, the same faint hiss was there. They cleaned the antenna. They removed pigeons that had been roosting in it. The hiss persisted. What they had stumbled onto was the afterglow of the early universe. The light from a moment, about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form, and for light to travel freely for the first time. That light, stretched by billions of years of cosmic expansion, now arrives at our radio antennas as faint microwave radiation. Almost the same temperature in every direction. Almost, but not quite. There are tiny variations, fractions of a degree, that map the seeds of all the structure we see today. This light is, in a sense, our most direct view of the early universe. It is also, in some interpretations of the universe inside a black hole picture, our most direct view of conditions near the horizon of our parent black hole. Whatever it is, it surrounds us. It has surrounded us all our lives. It is part of the steady backdrop of cosmic existence. There is nothing to do here. There is nowhere to be. The universe will still be turning when you wake. The stars, whichever stars they turn out to be, are still there. They have been there for a long time. They will be there for a long time still. They do not need anything from us. They are very quiet. They have always been very quiet. They do not mind whether we understand them or not. They go on in their slow turning in their long lives in the dark. And whatever encloses them, a horizon, an edge, a parent universe, or simply the inward curve of empty space itself, also goes on. Quietly, patiently, without urgency. There is no hurry. There has never been any hurry. The night will hold the question for as long as it needs to be held. The morning, when it comes, will not have answered it. Neither will the next morning. Neither will the next. But that is all right. The question, like the cosmos, is patient. It does not need to be answered. It only needs to be carried, gently, the way one carries any old and beautiful thing, with care, with attention, with no particular hope of ever fully understanding it. The dark continues. The stars continue. The horizon continues. And whatever lies beyond it, if anything lies beyond it at all, continues too, in its own slow and unreachable way. There is nothing more to say. The thought has settled. The night has settled. Sleep now. The cosmos does not need watching. It will be there in the morning exactly as it has always been.